Good evening, Carolians. This is Ancient Light. As you can see from the subtitle here, I'm talking about imaging a quasar without using a telescope. So I'm going to start with a description of what I would call a lockdown challenge. Some of you might be aware that we're in the middle of a pandemic. In early 2020, life as we knew it, of course, changed, and we went into life in lockdown. And this little object on the left caused the appearance of a lot of objects on the right. All over the pavement, all over building floors, all over supermarkets, we saw little signs like this down on the ground, reminding us where we should put our feet. But the words of Stephen Hawking resonated whenever I looked down at this sort of sticker. He said, "Remember to look up at the stars and not down at your feet. Try to make sense of what you see." So when George in Bromsgrove Astro said that he had seen a very distant object in his telescope, it got me thinking. Yes, the universe is of course vast and ancient, and we know that large telescopes, either large professional telescopes or even large amateur telescopes, have imaged galaxies that might be billions of light years distant. But it got me thinking, is it possible to capture an image of one of these very remote objects that are many billions of light years distant? Is it possible to capture an image of one of these objects without using a telescope? Spoiler alert, yes it is, otherwise this is a really short talk rather than just a short talk. So I looked up a paper that published a quasar survey, a survey of lots of quasars that are in the sky. What is a quasar? Well, a quasar is the nucleus of a galaxy that emits enough light to be seen at very great distances, at the sort of distances we're aiming for, billions of light years. Nobody really knows what a quasar looks like up close and personal. Here's an artist's impression. And almost certainly the central engine that's producing all of the light from a quasar is a supermassive black hole. Matter is falling into this black hole, and on its way in, the matter gets very hot and emits light right across the electromagnetic spectrum. From X-rays, ultraviolet, visible light, radio waves get emitted from such an object. So in this particular survey, I looked at all of the quasars that they were talking about, and I tried to identify one that was high in the sky as seen from the UK. This was the middle of last year, so I wanted an object that could be seen high in the sky during the summer months. And ideally, one of the most remote quasars that was described in this particular paper. And I found this quasar that goes under the wonderful name of 161737 plus 595020. Just rolls off the tongue, doesn't it? These professionals had taken a spectrum of this particular object, and a spectrum tells you how far away the object is, because the more distant objects are receding from us faster because of the expansion of the universe. The Hubble law, or the Hubble constant, tells us that the more remote objects are moving away from us faster than the closer objects. So if we can tell how fast it's moving, we can get an idea of how far away it is. How do we know how fast it's moving? We look at its spectrum and we see whether or not the various lines, the various peaks or troughs or features in the spectrum appear to be shifted from what we would expect. So here's the spectrum running from blue on the left-hand side to red on the right-hand side. It's not a coloured spectrum, it's just a graph showing how intense is the light at each of these wavelengths from 4,000 angstroms to 7,000 angstroms. An angstrom is 10 to the minus 10 meters, or 1/10 of a nanometer. And I'm not expecting anybody to recognise what's going on in this spectrum, but the people who analysed this said, look at this here. This is at 6,500 angstroms, and that doesn't belong there, in the sense that if this object was not moving, if it was just a light source in a laboratory, that peak wouldn't occur at 6,500 angstroms, it would occur at 1,200 angstroms in the ultraviolet part of the spectrum. In other words, this peak really belongs way off to the left of this particular spectrum, and it's been shifted to the right, in other words, to the red end of the spectrum. So it's been red shifted from where it would be if this object is stationary to 6500. And we quantify the amount of the redshift by looking at the difference between where it would be, where this particular feature would be if the object wasn't moving, in this case 1200 angstroms, and where it's actually observed in the spectrum of the object, in this case 6500. We look at the difference of those two numbers and divide it by the original number. In other words, 1200 has been shifted to 6500, so it's been shifted by 5300. Divide that by 1200 and we get the number 4-ish, 4.3 it works out. So we quantify how much this spectrum has been shifted by the redshift, which is a number which in this case is 4.3 and a bit. And that number is quite large. In other words, we'll look at the distances shortly, but a redshift of 4 means that this particular object has had its spectrum shifted by a huge amount, and that means it is very, very remote. And we'll look at calculation of the distance in a few slides' time. But I thought this was a good candidate. A very high redshift indicating it's very remote, and this one happens to be high in the sky during the summer months. So I gave it a crack. This was in about the middle of July. I got my camera out. This is the camera that I normally use for wildlife photography and other daylight photography, this SLR camera and lens, and I put it onto a tracker, a star tracker. This particular one is an Ioptron sky tracker, this little white box here. Other sky trackers are available. In essence, they are simply a box containing some batteries and a motor, and the motor will drive the camera around at 1 revolution per day. So as long as you line up this particular motor drive with the Earth's axis, then as the Earth turns and the stars appear to move, so the camera will track the stars. If all goes well, it should track the stars quite accurately. There's a little polar scope there to try and get the tracker as accurately as possible lined up with the Earth's axis. So this is my camera, a Nikon D7500, and my lens of choice is a 300mm f4 telephoto lens. This is exactly the same setup that I have used in the past for safaris, for taking pictures of wildlife. The camera is in no way specialized or customized or modified for astrophotography. It's just a normal daylight camera and lens. And if this particular camera is capable of photographing zebras, the question is it equally capable of photographing a quasar which is on the other side of the observable universe? That's essentially the challenge I set myself. So I took the camera, put it on the tracker, took it outside my front door, tried to avoid a street light shining down into the lens, and I pointed the camera at this particular location in Draco. I looked up the coordinates of the object and pointed it to this particular area of sky. Right in the middle there, that's not the quasar is very faint. That's a 5th magnitude star right in the middle of that rectangle, which represents the field of view of this particular lens. And when I looked in a star atlas, I found that the quasar was conveniently close to a relatively bright star, which means I could see that star on the back of my camera, so I could make sure the camera was pointing in the right direction. I focused on the 5th magnitude star, and then I focused on a slightly fainter star to try and get the focus as precise as possible. The fainter the star you can see, the more accurately you can tell when that star is nicely in focus. So I pointed at that part of the sky and then started to take some images. I wasn't sure how long I'd have to expose for, not being quite clear as to exactly how much noise I was going to get in the image and how bright that quasar would appear. So I exposed for essentially as long as possible. In July, we don't get much of a night. Evening twilight tends to blur into morning twilight. So there was about 2 hours of darkness either side of midnight. So I took not one long exposure. Of course, with astrophotography, it's quite common to take a series of shorter exposures and then stack them together later. This particular night, there were actually some clouds going by, so I simply set the camera to take lots of 30-second exposures, And then the following day I went through them all and threw out the ones that had clouds passing by or the occasional satellite. In the middle of lockdown, you don't tend to get not very many aircraft, but still there were some satellites. So I threw away a few of the images and then stacked the remaining ones, giving me a total exposure of something like 2 hours. And again, there's the bright star in the middle. So I'm expecting the quasar to be somewhere in that box, preferably in the middle of that box if I've identified it correctly. So although I took this entire 3-degree field of view, I was only really interested in what's going on inside that box there. So I blew that up so I could see what was going on, and right where it should be, perhaps no surprise, is our mystery object. There is the quasar. So yes, it is possible to capture one of these very remote objects using this particular camera and telephoto lens. Most of the light from the quasar has actually been focused into about 1 pixel. If I blow up that central region, you can see that most of the light has actually gone into that 1 pixel. I've artificially brightened some of these neighbouring pixels just so you can see it a little more clearly, but a little more than half of the light went into the central pixel and a little bit of the light has gone into the neighbouring pixels. So although the camera produced an image with 20 million pixels, essentially only one of those pixels actually caught the light from the quasar. Just as a little bit of an aside, what sort of resolution could we expect from this particular 300mm f4 lens, and also what resolution could we expect from the camera? Well, a 300mm f4 lens, f4 means that the aperture at the front is 1/4 of 300mm, so that means it's an aperture of about 75mm, and when you work out what the resolution should be, assuming that the lens has no aberrations, assuming that I've paid enough that this lens is a good quality and is not producing blurred images, then the resolution of the lens would be about 9 microradians, 9 millionths of a radian. Physicists prefer radians, astronomers tend to prefer arc seconds as the angle, the smallest angle that can be resolved. So that works out to be a little less than 2 arc seconds. When we think about how big the pixels are in the camera, they're about 4.5 microns in size, and so if we convert that to an angle, we find that the pixels in the Nikon DSLR chip would give us a resolution of about 3 arc seconds. The seeing that night, I would guess, would be of order maybe a couple of arc seconds or so. So in other words, the resolution of the lens, the smallest thing the lens could resolve, the smallest thing that the camera could resolve, and the seeing conditions were all roughly the same at the level of about 2 arc seconds. And just to give you an idea of scale, if we imagine what would the Milky Way look like, even if we could see it, which we probably couldn't, if we took the Milky Way and placed it at the same distance as this quasar, many billions of light years away, how big would it appear? Well, the Milky Way would be the size of perhaps a couple of pixels, roughly speaking, about 6 arc seconds, a very rough back-of-the-envelope calculation. Whilst looking at that particular small crop from the central region I've taken here is less than perhaps 1% of the whole image. Although I identified the quasar right at the middle, I also realised that there are in fact a few other objects in this image. The image size here of this square is about 8 by 8 arc minutes, and I realised by comparing what I had taken with a digital sky survey, a Sloan digital sky survey, I realised that some of those are stars and some of them actually are galaxies. I don't expect you to be able to tell the difference because you need to look quite closely and compare with other survey data. Perhaps you can see that some of these blobs look a little bit elliptical and don't look very star-like. That's fine, those are galaxies. And that's a galaxy, but even some of these objects that look like they could be stars, they're actually galaxies as well by comparing with professional surveys. So as well as catching the quasar, I've actually caught 10 galaxies in that small little crop. And assuming that that is representative of the whole image, that would mean that the entire image, 3 degrees by 4.5 degrees, has probably captured about 7,000 galaxies in this exposure, which is why I've rather cheekily called it the Barrett Deep Field here. It's interesting to note that having taken this picture and captured perhaps 7,000 galaxies, that's actually about the same number as the number of galaxies captured in the Hubble Deep Field. I'm not claiming this is as good, but it's interesting to note that you can catch as many galaxies in a long exposure with a telephoto lens as the Hubble can using its 1 million second exposure of the Hubble Deep Field. So coming back to this question, okay, I've captured an image of an object that's very remote. But just how far is it? What is the distance to the quasar? Well, one thing you've got to bear in mind when you're dealing with very distant objects is the light has taken a considerable length of time to arrive at the camera, having been emitted by the object a long time ago. So you can imagine the light leaving this galaxy, this quasar, on its way to Earth, and you could say, right, that was the distance then, when the light left. But of course, a long time has passed, and while the light was on its way to Earth, the universe has continued to expand, and so that galaxy, that quasar, has been carried along by the expansion of the universe, and so has been moving away from us. So while the light was travelling, the distance to the quasar is now greater. And when the light finally arrives at Earth to make our image, the galaxy has moved on even further. So that's the distance that the galaxy is now at the point at which the light arrives at Earth. So when you talk about the distance, do you mean the distance when the light left? Do you mean the distance now that the light has arrived? Or do you mean the distance that the light itself has travelled on the way from the galaxy to Earth? And if you're considering how far has the light travelled, you have to remember that the light is travelling through space, and space is expanding as the light is travelling through it. It's a rather bizarre thing to get your head around, but it's a bit like saying, well, if you're swimming through water, that's fine, but what if the water itself is moving? It's a sort of analogy to the way we think about light moving through space when space itself is expanding. And a rather nice analogy that gives you a good idea of what we're talking about is to imagine an ant walking along a rubber band, and then as it's walking, you're stretching the rubber band. So if you ask the question, how far has the ant walked? You have to think about where the ant started, where the ant ended, and how much you've stretched the rubber band while it was walking. So you can see it's not necessarily an easy question to answer if you simply say, how far has the light travelled? Or how long has the light been travelling? You have to think about the stretching or the expansion of space. Well, that can be done because we have a reasonable understanding of how space has been expanding. We know, roughly speaking, what it's doing now. The Hubble constant tells us that if we measure the distance to a galaxy and how fast that galaxy is moving, then if we divide the speed by the distance, we get the Hubble law, and the Hubble constant tells us that for a given distance to a galaxy, we can work out how fast that galaxy is receding from us. And we can sort of wind the clock back and get an idea from our understanding of the physics of how the universe came to be and how the universe has been expanding ever since that light left the quasar for the last how many billion years. If we understand how space has been expanding, then we can work out where the galaxy was, where the galaxy is now, and what's happened to space in the intervening time. And that's what I've done here. I've tried to calculate for a given redshift, if we're observing a galaxy which is receding from us at a particular speed according to its redshift, then how far was it when the light left that particular object? That's the blue line. Where's that object now? That's the red line. And how far has the light travelled in order to get from the object to the Earth? That's the green line. And you can see it varies. If we have a very small redshift, if the object is quite close, then it doesn't really make a lot of difference as to whether or not we work out the distance then or the distance now. The difference between the red and the blue line down in this bottom left-hand corner, they're very similar if the light hasn't travelled for very long. But if we talk about large redshift, then the light has been travelling for a long time, and so there's a bigger and bigger difference between the distance then and the distance now. So if we think about our particular quasar is at 4.3 redshift, and that means that we have measurements of, values of, the distance then was about 5 billion light years, the distance now is about 25 billion light years, and it has taken the light about 12 billion years to reach us. Before saying anything else, I might add that if we don't look at the Barrett deep field, but instead we look at the Hubble deep field, then the Hubble deep field can go far beyond a redshift of 4. The Hubble deep field goes out to a redshift of 6 or maybe even 7. So it goes out considerably further. If we get rid of those lines and just think about the 3 values we've got for our quasar, let's remind ourselves of what these mean. The quasar was about 5 billion light years away when the light was emitted by the quasar. The light has been travelling for 12 billion years, more than 12 billion years. The universe is about 13.8 billion years old, which means the light that made the image I've just shown you has been travelling for something like 90% of the age of the universe. If we were to take the Hubble deep field and go out to redshift 6 or 7, instead of going back in time 90% of the way back to the Big Bang, we could go back 95% of the way back to the Big Bang. By swapping my telephoto lens for the Hubble Space Telescope, I could get 5% further back in time. That's a very expensive way of gaining an extra 5%. But sticking with our quasar, whilst the light was travelling, the universe continued to expand and hence took the quasar even further away from us, such that by the time the light actually arrived in that July night, the quasar was then 25 billion light years away. But just looking at these rather mind-boggling numbers, we come to a very interesting conclusion. How far has the galaxy moved in between when the light left and when the light arrived? It started out at a distance of 5-ish billion light years, and it ended up at a distance of 25-ish billion light years. And it's changed its distance by 20 billion light years in a time period of 12 billion years. And so if we just do a very quick back of the envelope calculation, during the 12 billion years that the light took to reach us, the quasar's distance has increased by more than 12 billion light years. Speed is just distance over time, so if it's travelled a distance of 20 billion light years in 20 billion years, that means it's been motoring along at about 1.6 times c, the speed of light. This quasar has been receding from us faster than the speed of light. That is a rough indication of its average speed, but given that we have an idea of how the universe has expanded, we can actually calculate by going back in time to 5 billion years after the Big Bang, 1.4 billion years after the Big Bang, when the quasar was 5 billion light years away. We can actually calculate how fast was it moving then and how fast is it moving now. On average, it must be about 1.6 times the speed of light. But using those curves I showed you before, we can actually calculate what the speeds were. And it turns out that when the light left the quasar was receding from us at more than twice the speed of light, 2.2 times c. It's now receding from us at about 1.7 times the speed of light. Now, as the universe expands, you might assume that, well, gravity is pulling on everything. So although the Big Bang threw everything out and made space expand, surely gravity is pulling back and slowing things down. Well, sure, to start with, it did slow the quasar down and its velocity dropped. but it didn't continue to drop. After initially slowing down, for the last few billion years, the quasar's speed has actually been going up. The quasar is accelerating away from us. It's not moving away and slowing down because of gravity. It's as if there is some other force out there, some anti-gravity, if you like, which instead of slowing down the expansion, is speeding up the expansion and accelerating the velocities of these distant objects. This is what we call dark energy. Just because we have a name for it doesn't mean we understand it. Something is pushing that curve up instead of allowing the curve to come down. Something is making these distant objects move even faster. And dark energy is what we call it, but we have no real understanding of why dark energy exists and what it's actually doing to the universe. If we think about the light's journey, there's us here and now. The horizontal scale is distance from us, so we are of course at 0, and the vertical scale is time since the Big Bang. So there's us 13.8 billion years after the Big Bang, and we are at 0 on space. If we go back in time 12 billion years, there's the quasar at a distance of 5 billion light years from us. And if we think about the light travelling from the quasar to us, we might think, well, isn't that the easiest route? Won't the distance from the light to Earth simply get smaller and smaller and smaller as time goes by? In other words, as we go higher and higher in this diagram, won't the light simply get closer and closer and closer to us? Well, remember the universe is expanding. Remember the swimmer swimming against a tide. Remember the ant moving on a stretching rubber band. Because the quasar is receding from us at something like twice the speed of light, space is stretching, so although the light is trying to make headway towards us, the light is actually being dragged backwards. It's a really weird thing to think about. So although the light is trying to make headway towards us, because it's moving through space and space is expanding so fast, for a while the light actually gets dragged backwards. So the light is emitted from the quasar, and a billion years later the light is further away from us. Even though the light is trying to come towards us, for a few billion years the light is actually further away from us than the original distance to the quasar. For 2 to 3 billion years the light is getting further away, and eventually the light starts to make some headway and ends up arriving here and now at our location 13.8 billion years after the Big Bang, roughly 12 and a bit billion years after the light left. That's what the light was doing. What was the quasar doing? Well, whilst the light was making that 12 billion year journey, the quasar got further and further and further and further away from us, and it went zooming off, such that by the time we get to now, at 13.8 billion years, we find the quasar is way off to the right hand side at something like 25 billion light years. I've shown it as a dotted line. Remember what I showed earlier, the velocity of the quasar is actually changing. So given that this is distance and time, so the gradient gives us the speed of an object, if we know the speed of the object is changing, then that line shouldn't be a straight line, it should be slightly curved, slightly wavy. And I didn't want to try and draw that accurately, so I've just given an indication of what that quasar is doing. The light gets dragged backwards and then arrives at Earth. Meanwhile, the quasar shoots off at great speed into the void. Let's just think about that whole journey from the perspective of the light that left the quasar. The light was emitted by the quasar 12 point something billion years ago. That's about 1.4 billion years after the Big Bang itself, very early in the history of the universe. For a few billion years it was dragged backwards, eventually it started to make some headway. It had been travelling for nearly 8 billion years before the Sun and the Earth were actually born. and then it continued on for a few more billion years. Life evolved on Earth, the light travelled on. Dinosaurs came and went, the light travelled on. In the last million years of its very long journey, it arrived at the edge of the Milky Way, crossed a few spiral arms, entered the solar system, and in the last few hours it arrived at Earth, travelled through our atmosphere in a fraction of a second, hurtled towards England, dodged a few clouds, entered the lens, hit the camera, and produced the image that I showed you earlier. Just a pixel in the image, but what a journey. So here's a graphical summary, if you like, of what I've been talking about. The main image is the image I took using this camera and telephoto lens on a little star tracker. I pointed it in the direction of the constellation of Draco. You can see it's just next to Ursa Minor there with Polaris on the right. And the inset in the top right shows a region just near this 5th magnitude star, and there is the quasar that I've managed to image in just about 1 pixel, even though that quasar is sitting at a distance of 25 or so billion light years, and the light that produced that little dot, that little pixel, has been travelling for 90% of the age of the universe over 12 billion years. So, in terms of the challenge, is it possible to capture the light from a distant object like this, not using a telescope, but just using a camera and telephoto lens? There's the evidence. So yes, it is possible for an ordinary camera to capture what I like to think of as a quasar's ancient light. Thank you all for listening.